Hello everyone, and welcome to our next video where we're going to be discussing alcohols. So alcohols are a class of compounds that are really widely used. They have a range of applications and functions. However, what we'll see is that even small changes in the structure of the alcohol can greatly affect the function. So let's start just real quickly taking a look at some of the alcohols that we have drawn on the screen. So first up we have methanol. Right? Methanol, sometimes referred to as wood alcohol, is poisonous to consume, but it is the feedstock for numerous compounds. If we move to the next one and add just one carbon to our chain, we get to ethanol, which is not necessarily poisonous to consume and is regularly consumed. This is also a fuel and a solvent for compounds that aren't necessarily always soluble in water. So if we change the structure by adding an OH group to the second carbon, we end up at ethylene glycol, right? So this is a diol. So this is also commonly referred to as antifreeze and is again poisonous to consume. So just adding an OH group to our ethanol changes the function and the toxicity of the compound. I will point out that ethylene glycol is also a viscous liquid, unlike ethanol. If we then move up and add one more carbon and one more OH group, we get to the compound glycerin, which is another lubricant that is also used in the making of explosives. Also the title of a Bush song. All right, so before we get into talking about the physical properties and some of the things that allow these molecules to change their function so quickly, let's talk about the terminology that we're going to use in referring to alcohols. So the terminology we are going to use is based around describing the number of carbons attached to the carbon that is attached to the alcohol. Right, so this alcohol here is referred to as a primary carbon or primary alcohol because it has a carbon that is attached to one other carbon. Our second in the line is known as a secondary alcohol because the carbon here is attached to two carbons. And finally, we have a tertiary alcohol where our central carbon is attached to one, two, three other carbons. Right, so again, based on the number of alkyl groups attached to the carbon with the OH on it. So that's it for terminology, pretty straightforward. Next up, we'll talk about the physical properties of alcohols. So in looking at this, we're just going to start with a simple alcohol. We'll start with methanol. And one of the key things to note about alcohols is that the oxygen is much more electronegative than either of the atoms it's attached to. Right? So this will create dipoles in the molecule, which pull electron density towards the oxygen and away from the hydrogen and the carbon. So these will be electron deficient. This will be electron rich. This also creates a dipole moment in the overall molecule. So this pulling of electron density away from the hydrogen allows alcohols to have a special characteristic of hydrogen bonding. Right, so if we look at our alcohol, again, I'll just draw it here. This electron deficient hydrogen can interact with the lone pairs on another oxygen in a favorable way. And this is known as a hydrogen bond, shown as a dashed blue line. Right? So in this case, we would use the terms hydrogen bond donor and hydrogen bond acceptor to describe the molecules involved in this interaction. So the lone pair is accepting the hydrogen in that hydrogen bond. The alcohol where the hydrogen is involved in the hydrogen bond is the donor. It's donating that hydrogen into the interaction. Right? So another important thing to remember about these molecules is that while we've drawn one interaction above, in fact, this is a network of interactions right? So alcohols act as both hydrogen bond donors and acceptors. And they are both simultaneously, right? So this is a fairly strong intramolecular force, which means that this is going to increase the boiling point of these compounds relative to the corresponding hydrocarbons, right? Because these are strong forces, which means we have to add more energy to break them apart. So hopefully that reminds you of things you learned in first year. All right, so the next thing we're going to do is talk about the two parts of an alcohol. We have this molecule can be divided into two parts. The alkyl part and the hydroxyl part. This is hydrophilic, whereas the long alkyl chain will be hydrophobic, which means that the solubility of our compounds is going to be heavily dependent on the length of this carbon chain. So if we're considering the solubility, we're going to see that this solubility will decrease as carbon chain length increases. We can see this in comparing, let's say, ethanol with heptanol, or, well, no, we'll go with pentanol. That's the one I have data for. All right, so ethanol is essentially infinitely soluble in water. Whereas when we increase the chain length, what we're going to see is that this drastically decreases the solubility in water. And that's because of the hydrophobic nature of our carbon chain. And notice that we've only increased our carbon chain by, 3 carbons? This isn't a huge change. All right, so the next thing we're going to talk about in relation to alcohols is their acidity. So hopefully you've already watched the videos on pKa's. Alcohols have a moderately acidic hydrogen, right? So the pKa of an alcohol is between like 15 and 20. What this means is that if we take something like ethanol and react with a hydroxide, something like sodium hydroxide, we compare the pKa's of these, we see this is 15.9 for ethanol, 15.7 for water. This reaction is actually going to be reactant favored, so you're not going to have a useful concentration of your alkoxide, right? So you cannot form alkoxides very easily or in a useful quantity with sodium hydroxide. You need a stronger base. So methods for deprotonation of alcohols. You can use something like a hydride source. This is known as sodium hydride. And that will generate hydrogen gas. So this was, again, another driving force for the formation of your alkoxide. We can also look at pKa's. This is 15.9. pKa here is roughly 36. So this reaction will be driven towards the product side, both due to the release of gas and because of the pKa's. You can also use metals. Generally sodium, lithium, or potassium. And this will give you a reaction that looks something like this, where M is your metal. To again give you hydrogen gas being released. All right, so in general, you're going to need a stronger base than hydroxide to deprotonate an alcohol. But that, again, will depend on the pKa that you're dealing with, right? So keep in mind that we've had to do this because the pKa of water is 15.7, whereas the pKa of ethanol is 15.9. So those are very close. However, we've talked about the fact that the pKa's of alcohols range from 15 to 20. So let's talk a little bit about pKa trends and the factors that influence pKa's of alcohols. All right, so the first factor that we are going to consider is resonance. So we've covered, again, resonance as one of the things that we consider when we're looking at pKa trends in a qualitative manner. We'll do that again here. So let's compare the pKa's of cyclohexanol, which is the pKa of approximately 17, where phenol has approximately a pKa of around 10. So why this large difference in the pKa's of these systems? Well, why? Well, to answer that question, let's look at the conjugate bases. So here, if we look and compare the conjugate bases, we see that while the lone pairs on the oxygen here are stuck on our cyclohexanol, right, because they're attached to an sp3 hybridized carbon, there's no resonance involved in this molecule. So the oxygen is stuck holding that full negative charge. In phenol, we can move one of these lone pairs down and push the lone pair onto a carbon to share the charge across the ring. Right? So we can continue pushing this around. It's going to share the electron density of that negative charge across the ring system. Right? So the negative charge is delocalized. And therefore, this is better able to handle the negative charge, and it doesn't need the proton as much. Right? So resonance is one way in which we can affect the pKa of an alcohol. One thing I will point out is if we then look at this equation, remember we compared this earlier with ethanol and said that sodium hydroxide was not a strong enough base to give large quantities of the alkoxide. If we compare the pKa's now, notice that this reaction has turned from something that's almost equal on both sides to something where the product has a much more favorable state, right? The pKa of water is much larger than the pKa of the phenol, so this is now a strong enough base to deprotonate our phenol. So phenols deprotonated by weaker bases. Okay. All right, so that's one of the factors. The next one that we're going to talk about is induction. So we've already covered this, so we'll briefly just talk about how this can affect alcohols. Right? So here the pKa is 16, here this is 12. Why? Well, again, we look at the conjugate bases. We see that this is pulling electron density away, which allows the electron density of the oxygen to be shared across the carbon backbone a little more than in ethanol. So an inductive effect there. So the last one is one that we haven't covered yet, and that is the influence of the environment. Remember that we're measuring pKa's in water. So solvation is going to play a role. How the molecule interacts with water will influence how willing it is to give up a proton. So let's compare ethanol and T-butoxide, or T-butanol. So we have a slight pKa difference here, despite the fact that these are both alcohols attached to sp3 carbons. So why? Well, again, we look at the conjugate base. So if we look at ethanol, this molecule has a fairly large area. Draw it a little differently. To interact with the solvent, right? So it can hydrogen bond in all of these directions. Whereas if we look at T-butanol, right? Keep in mind that each of these has 3 hydrogens associated with it. So this is a fairly bulky group. That means that this molecule is going to have a smaller area in which it can interact with solvent. Now, these hydrogen bonds that we're showing allow the electron density from that O- to be shared through hydrogen bonding. Which means that the more hydrogen bonding you have, the more stabilized that negative charge will be. So a smaller surface area that we see in our T-butoxide means that it has less hydrogen bonding and therefore is less stabilized. And therefore it wants to keep its proton a little more than ethanol, which is more willing to give it up because it can form more hydrogen bonds. Right, so this is the first time that we've introduced a force of the environment influencing the pKa. So solvation can influence the pKa of your alcohol. Okay, so with that, that concludes our discussion of alcohols and their properties. Next up, we'll talk about amines.